Okay, let's unpack this. Today, we're diving into something foundational, really, for understanding how things flow. The Navier-Stokes equations.
Yes, they're absolutely central. Named after Claude Louis Navier and George Gabriel Stokes, of course. They essentially take Newton's second law, EFMA, and apply it to fluids.
Right, to substances that move and deform. But there's a key element they include that simpler models leave out,
Ah, yes, viscosity. That internal friction, the stickiness within the fluid itself, that's what makes them different from the older Euler equations.
which only model ideal fluids, right? No friction.
Exactly, in viscid flow. But real-world fluids, whether it's air or water or honey, they have viscosity. And because Navier-Stokes accounts for this, well, they become an incredibly powerful tool.
Powerful for engineers, I imagine. You need that real-world accuracy.
Absolutely indispensable. Think about modeling weather patterns, huge ocean currents. These equations are underneath those models.
Wow, okay, so massive scale.
hmm And also, very practical engineering. Water flowing in a pipe, air moving over a car body or an airplane wing, that's all Navier-Stokes.
Designing cars, predicting lift on a plane.
Even things like blood flow in arteries, it's really widespread.
Okay, so incredibly useful. But I understand the mathematics itself gets, well, pretty complicated.
It does. In their general form, we're talking about nonlinear partial differential equations. That nonlinearity is the tricky part.
Nonlinear meaning the different parts of the equation sort of feed back into each other. It's not a simple cause and effect.
That's a good way to put it. A key source is something called convective acceleration. It's about how the fluid's velocity changes just because it's moved to a different position, maybe where the flow speed is naturally higher or lower.
Like water speeding up as it goes through the narrow part of a hose.
Exactly like that. And mathematically, this term is what allows the equations to describe, well, the chaos of turbulence.
Ah, turbulence, that swirling, unpredictable motion you see everywhere. So Navier-Stokes can model that, but it's hard because of the nonlinearity.
Extremely hard. Turbulence involves motion on so many different scales simultaneously, from large eddies down to tiny whirls. Solving that analytically is, well, usually impossible. We rely heavily on computer simulations.
Which brings us to a really fascinating point, maybe even a bit unsettling. Before we get to that big mathematical question mark, though, just want to mention that this deep dive is brought to you by embersilk.com. If you're looking into AI education or integration, check out embersilk.com.
Right. So back to that unsettling part. Despite how essential these equations are in practice.
We don't actually know for sure if they always work perfectly, mathematically speaking, at least not in 3 dimensions.
That's the core of it. It hasn't been proven mathematically whether smooth, well-behaved solutions always exist for any starting condition in 3D.
Smooth meaning the fluid's velocity or pressure doesn't suddenly shoot up to infinity somewhere. It doesn't just break.
Precisely. Do the solutions remain physically realistic, or can they develop these mathematical singularities, these blow-ups? We assume they don't for practical purposes, but there's no rigorous proof.
And that is the Navier-Stokes existence and smoothness problem.
It's considered one of the biggest open questions in mathematics. So much so that the Clay Mathematics Institute listed it as one of their 7 Millennium Prize problems.
With $1 million prize attached, right?
Yes, $1 million for either a proof that smooth solutions always exist or a concrete example, a counterexample showing a situation where they do break down.
So let's just recap. We have these equations, vital for everything from designing airplanes to predicting storms.
The absolute bedrock of modern fluid dynamics and engineering.
Yet, at their mathematical heart, in the full complexity of 3 dimensions, there's this fundamental uncertainty. We haven't nailed down if they are always guaranteed to give sensible answers.
It highlights a fascinating gap, doesn't it?
Yeah.
Between physical intuition and mathematical proof. We observe fluids behaving smoothly, we build technologies based on these equations assuming smoothness, but the ultimate guarantee isn't there yet.
It really makes you think. If the basic rules governing something as common as water swirling out of a tap hold this deep mathematical mystery about guaranteed predictability, what does that suggest about our ability to truly predict, the really complex, chaotic systems we see everywhere in the world? It's quite profound.